Conducting polymers, CPS, are organic materials characterized by a conjugated pi-electron backbone that enables metal-like conductivity or semiconducting behavior, typically enhanced through chemical or electrochemical doping. In their pristine state, CPs are generally insulators or semiconductors. Upon doping, their conductivity can increase by several orders of magnitude due to the formation of mobile charge carriers, electrons and holes, along the delocalized conjugated system. CPS combine electrical conductivity with the lightweight, flexible, and easily processable characteristics of conventional plastics. They also exhibit optical and electronic properties comparable to inorganic semiconductors and metals. These materials can be synthesized using simple, versatile, and cost-effective methods, and can be assembled into multifunctional supramolecular architectures, particularly via electropolymerization. Representative CPS include polyacetylene, polyaniline, PANI, polypyrrole, PPY, polythiophene, PTH, poly-3,4-ethylene dioxythiophene, PEDOT, and polyphenylene. Charge transport mechanism. Electrical conductivity in CPS arises from delocalized pi-electrons within an unsaturated polymer backbone. The conjugated system forms an electronic pathway for charge transport. Doping introduces charge carriers, polarons, bipolarons, dramatically enhancing conductivity. Thus, CPs provide a unique combination of electronic transport and polymeric mechanical properties. Synthesis methods. Conducting polymers are synthesized using multiple approaches, enabling control over morphology, conductivity, and application-specific performance. Chemical oxidative polymerization, electrochemical polymerization, vapor phase polymerization, template-assisted synthesis. Plasma polymerization, for thin, pinhole-free films adhering to diverse substrates without solvents. Property tuning is achievable through synthetic control. For example, optimized PANI can exhibit specific capacitances of approximately 300 farads for energy storage applications. Classification and representative conducting polymers. CPS are commonly classified according to their charge transport mechanisms, including conjugated pi-electron systems, conductive nanomaterials, and ion-conducting polymers. The most widely studied class comprises conjugated pi-conductive polymers. Polyacetylene, PA. The development of polyacetylene and related conductive polymers led to the 2000 Nobel Prize in Chemistry, awarded to Alan J. Heeger, Alan McDiarmid, and Hideki Shirakawa. Polyacetylene consists of a linear polyene backbone with alternating double bonds. The repeated hydrogen units permit mono or disubstitution, enabling structural and functional modification. Functional derivatives demonstrate electrical conductivity, photoconductivity, gas permeability, supramolecular assembly, chiral recognition, helical nanofiber formation, and liquid crystalline behavior. Polyacetalenes are sometimes associated with acetylene black, AB, a carbon nanomaterial produced by controlled acetylene combustion under pressurized air. AB is widely used as a conductive additive in carbon paste electrodes and electrode modification systems. Polypyrrole, PPY. PP is a biocompatible conducting polymer valued for its high conductivity, redox activity, environmental stability, and ease of synthesis. Applications include neural implants, biosensors, and molecular memory devices. Structurally, PPY is amorphous and insoluble. First obtained in 1963 via pyrolysis of tetraiodo-pyrrole, PPY is commonly synthesized by oxidative polymerization of pyrrole using ferric chloride in methanol or by electrochemical polymerization at an anode. Electrochemical synthesis enables nanoscale sheet formation on electrodes. However, scalability for mass production remains challenging. Copolymerization with functional monomers enhances processability and functionality. Polythiophene, PTH. Polythiophene exhibits stable and tunable conductivity depending on dopant type and polymerization conditions. Conductivity correlates with conjugation length. Oligomers containing approximately 11 thiophene units show conductivity comparable to high molecular weight PTH. Because conjugated polymers are typically non-transparent, transparency can be improved by dilution strategies such as block copolymerization, alkyl side chain grafting, blending with transparent polymers, or forming composites within insulating matrices. Plasma polymerization and thin layer deposition enable formation of thin, adherent, solvent-free films. PTH can be synthesized electrochemically, film formation at the anode, in thiophene/electrolyte solutions, or chemically using suitable catalysts. Electrochemical routes eliminate isolation steps, but may suffer from irreversibility or degradation. Poly 3,4-ethylenedioxythiophene, PEDOT, and PEDOT:(PSS). PEDO is formed by 2,5 coupling of 3,4 ethylenedioxythiophene monomers, producing linear conjugated chains with high conductivity and mechanical flexibility. Pristine PEDOT is insoluble. Therefore, it is commonly combined with polystyrene sulfonate, PSS, to form PEDOT:(PSS). PSS acts as both dopant and stabilizer, coating PEDOT to generate nanoscale particles dispersed in water as stable colloids. PEDOT:(PSS) is a p-type semiconductor valued for electrical conductivity, solution processability, and visible transparency, making it highly suitable for optical and electronic devices. Polyphenylene. Polyphenylene contains aromatic rings in its backbone and is typically obtained as an insoluble powder with notable thermal, chemical, and electrical properties. Conductivity enhancement has been explored through hybridization with ZNO nanoparticles, silicate platelets, polystyrene blends, amino/carboxyl functionalization, poly-L-lysine, and diphenylamino S-triazine derivatives. Electrochemical strategies have been developed for activating nucleophilic fluorination of cationic intermediates, including automated remote-controlled 18F fluorination platforms. Studies also examine physicochemical properties of polyphenylene sulfide derivatives incorporating ZNO nanoparticles. Polyaniline, PANI. PANI is among the most promising CPs due to simple synthesis, high conductivity, environmental stability, and tunable electrical properties via protonation or charge transfer doping. It is widely applied in sensors, pH-responsive biomaterials, redox active systems, and nanocomposite matrices. PANI exists in 3 idealized oxidation states: leucoemeraldine, fully reduced, poorly conductive; emeraldine, partially oxidized, most stable and conductive upon acid doping; pernogranulin, fully oxidized, poorly conductive even after doping. Synthesis typically involves oxidative polymerization of aniline using ammonium persulfate in acidic media. The process is exothermic and yields a mixture of oxidation states, with acid-doped emeraldine being the most conductive and stable form. Organic-inorganic PANI nanocomposites enable control of electrical, magnetic, mechanical, and thermal properties. Applications. Conducting polymers are used extensively in energy storage, batteries and supercapacitors, organic electronics, OLEDs, solar cells, transistors, biomedical devices, biosensors, drug delivery systems, neural probes, sensors, electrochemical, gas, and chemical sensing of volatile compounds, ions, and biomarkers, functional coatings, anti-static layers, EMI shielding, corrosion protection. By integrating electronic functionality with polymer processability, CPs bridge the gap between metals and conventional plastics, enabling multifunctional materials for advanced technological applications.